Welcome back to the energy conversion lectures. In this lecture and the coming lecture, we will give some introduction about the synchronous machines. Basically, we will give a general idea about the construction and some important fundamental concepts about the synchronous machine. Synchronous machine is one of the important types of AC electrical machine. This figure shows the side view cross-section of the synchronous machine. Synchronous machine consists of two main parts, stationary part and rotating part. Between the stationary part and the rotating part, there is an air gap to allow for the rotation. Note that the air gap of the actual machine is very small. The stationary part called stator or armature and the rotating part called rotor. The stator consists of magnetic material core and windings. The core of the stator is made of thin insulated laminated magnetic materials to reduce the eddy current loss and therefore reduce the heat inside the machine. The stator windings or coils can be called armature windings. The armature windings are usually a three-phase AC windings. The output terminals of the armature windings are connected to three-phase AC system or supply. In general, the term armature is used to refer to the windings on a rotating machine which carry AC currents. Also refer to the windings where the main voltage component of the machine is induced. The stator windings or armature windings of the synchronous machine are designed for high voltages and currents. In case of the rotor is made of magnetic material core and rotor winding. The rotor core can be laminated or solid magnetic material, depends on the rotor types, as we will see later. The rotor winding can also be called the field winding because the rotor winding is used to produce the main operating magnetic field when it is excited by DC current. We will learn later that this rotor main magnetic field will produce the main voltage component in the stator winding of the synchronous machine. The combination of the rotor core and the rotor winding can be called the field system. The field winding or coil is fed by DC current. This DC current is fed through two carbon brushes B1 and B2 slip on two rotating slip rings S1 and S2 as shown. The two slip rings are mounted on the rotor shaft and the brushes slip on them. The slip rings are metal rings completely encirculating the machine shaft but insulated from the shaft. It should be noted here that the system used to excite the rotor field winding with DC current through the brushes and the slip rings is called the DC excitation system. This DC excitation system type shown in this figure is external type and is usually a rectifier. This figure shows synchronous machine with another type of DC excitation system which can be mounted directly on the shaft. Basically, this excitation system is a small machine generates three-phase AC voltage connected to a rotating rectifier also mounted on the shaft to generate the DC excitation current. This excitation system does not use slip rings and brushes and is usually used in medium power level machines. The DC current flowing through the DC winding of the rotor is called field current and can be denoted by IR. The DC field winding represents the low power side of the machine. Basically, the DC power required for the DC field excitation is low, and it is only around 1% or few percent of the main power rating of the synchronous machine. It should be noted here that the rotor magnetic field of the synchronous machine can be produced by using field winding and DC current or by using permanent magnets. Synchronous machine with permanent magnet is called permanent magnet synchronous machine, while synchronous machine with field winding can be called wound rotor synchronous machine. Basically, the permanent magnet of the rotor will produce the main magnetic field of the machine. Note that the permanent magnet synchronous machine does not require brushes and slip rings and DC exciter. The focus of our lectures in this chapter will be only on synchronous machines that have rotor with field windings. In other words, we will focus on the wound rotor synchronous machine. Note that wound rotor synchronous machine and permanent magnet synchronous machine share same principles and concepts. So understanding wound rotor synchronous machine give us big idea about the permanent magnet synchronous machines. The rotor of synchronous machine can be divided based on their construction into two types: salient pole rotor and cylindrical pole rotor as shown. The salient pole rotor is usually made of laminated magnetic material and usually has large diameter and small length. The field winding of the salient pole rotor is concentrated winding type. Concentrated winding type means the winding is wound around the rotor in one big multi-turn coil as shown. Synchronous machine that uses salient pole rotor type is usually used in low-speed applications such as hydro generator. Synchronous machine that uses salient pole rotor type cannot be made strong enough to withstand high speed. Also, salient pole machine would cause excessive windage loss at high speed and would tend to produce noise. When the DC current passes through the field winding, the rotor generates DC field and the rotor becomes electromagnet. That means the rotor becomes big magnet with north and south poles when it is excited. The rotor and its field winding in this figure represents two poles salient pole rotor. Practical machines of this type of rotor are usually consist of 6 to 120 poles. The direction of the DC current determines the direction of the rotor magnetic field and therefore the rotor poles. By varying the magnitude of the DC excitation current, we can vary the strength of the magnetic field. To simplify this drawing of the two poles salient pole rotor, the drawing can be represented by rotor core with two poles, north and south poles as shown. This figure shows the 4 poles rotor construction of the salient pole rotor. As we can see, the rotor has 4 poles, 2 north poles and 2 south poles. Each pole consists of one concentrated coil of 2 turns. The 4 concentrated coils of these 4 poles rotor are connected in series. This figure shows the simplified form of the 4-pole salient pole rotor. In case of cylindrical pole or non-salient pole rotor, the rotor core is usually made of non-laminated solid core of magnetic material and they are usually small diameter and has large length. The field winding of the cylindrical pole rotor is distributed winding. Distributed winding type means that the winding is distributed in different slots as shown. This figure shows 5 coils distributed in slots and connected in series. Each of these 5 coils could have 1 turn or n turns. Normally, 2/3 of the rotor periphery or rotor circumference is slotted to accommodate the winding. The remaining 1/3 unslotted portion of rotor periphery acts as the poles. Synchronous machine that uses cylindrical pole rotor type is usually used in high-speed applications because it is mechanically balanced, such as in turbo generators, which are driven by steam turbines. When the DC current flows through the field winding, the rotor generates DC field and becomes an electromagnet. That means the rotor becomes big magnet with north and south poles. The rotor and its field winding in this figure represents 2-pole cylindrical pole rotors. Practical machines of this type of rotor are usually consist of 2 to 4 poles, and the speed varies between 1500 revolutions per minute to 3000 revolutions per minute. The direction of the DC current determines the direction of the rotor magnetic field and therefore the rotor poles. By varying the magnitude of the DC excitation current, we can vary the strength of the magnetic field. To simplify this drawing of the 2-pole cylindrical pole rotor, the drawing can be represented by rotor core with 2 poles, north and south poles as shown. This figure shows the front cross-section of 4-pole cylindrical pole rotor. As we can see, the rotor has 4 poles, 2 north poles and 2 south poles. Each pole has 2 coils connected in series, and all coils of the 4 poles are connected in series. This figure shows the simplified form of the 4-pole cylindrical pole rotor. It is very important to know that the rotor type of synchronous machine impacts the air gap characteristics, stator self-inductance characteristics, and torque characteristics of the machine. Let's give some idea about this point. Assume we have the following 2 cross-section synchronous machines. The first machine consists of stator and 2 poles Salient pole rotor. The second machine consists of stator and 2 poles cylindrical pole rotor. As we can see, the major difference between these 2 machines is the rotor type. Therefore, let's focus on the rotor of these 2 machines, and we will cover the discussion of the stator in the coming lecture. One of the important differences between these 2 machines is that the Salient pole rotor machine has non-uniform air gap, while the cylindrical rotor pole machine has uniform air gap. As we can see, in case of the Salient pole rotor machine, the air gap is minimum along the pole's axis, while the air gap along the interpole axis is maximum. However, in case of the cylindrical pole rotor machine, the air gaps along the pole axis and the interpole axis are same. Based on this difference between the salient and non-salient rotor, the stator self-inductance, or more specifically, the stator magnetizing inductance of these two machines will be as shown. As we can see, the inductance of the salient pole machine changes with rotor position, while the inductance of the cylindrical pole machine is constant with the rotor position. Also, the torque of the salient pole machine will have two components, the mutual torque component and the reluctance torque component, while the cylindrical rotor machine will have only one torque component, which is the mutual torque component. Please review the following lectures to get better idea about the relationship between the air gap and the stator self-inductance and their impact on the generated torque components of the machine. It should be noted here that the axis along the pole's axis is called d-axis, and the axis along the interpole axis is called the q-axis. Note that the interpole axis is the axis between two poles axes. In case of four poles machines, the d-axis and the q-axis of the salient and non-salient pole machines are as shown. It should be noted here that the angle between the north and the south poles is always 180 degrees in electrical angle. The electrical angle can be represented by theta E. The electrical angle in case of the two poles machine is equal to the mechanical angle theta m. Basically, the mechanical angle is the angle measured in space between 2 points around the machine. However, the electrical angle depends on the number of poles of the machine. So in case of the 4 poles machine, the angle between the north and south is still 180 degree electrical, while the mechanical angle is equal to 90 degree. In other words, theta E is equal to 4/2 times theta m, or theta E equals 2 times theta m, where the number 4 is the number of poles. Based on this example, we can introduce very important relationship between the electrical and mechanical angles as shown. The electrical angle theta E is equal to half the number of poles of the machine times the mechanical angle theta m. I would like to add here that the rotor d-axis and the rotor q-axis are always perpendicular with respect to each other. That means the angle between the rotor d-axis and rotor q-axis is always 90 degrees apart in electrical angle. Now let's move on to some other general information about the synchronous machine. We mentioned earlier that synchronous machine has two excitation windings, the AC windings and the DC winding. The DC winding is excited by DC current and the AC windings are excited by AC currents. Since we have two excitation windings and two excitation currents, the synchronous machine is considered a doubly excited magnetic system. Synchronous machine can operate as synchronous generator, sometimes called alternator, or as synchronous motor. Synchronous generators converts mechanical energy input to electrical energy output. The mechanical energy input fed through the shaft of the machine and can be represented by mechanical speed and mechanical torque. The shaft of the machine is connected to a device usually called prime mover through a mechanical coupling. The prime mover can be steam turbine, nuclear turbine, gas turbine, hydro turbine, and internal combustion engine. Basically, these turbines convert different energy sources such as coal, nuclear, gas, hydro energy, and petroleum, oil, to mechanical energy represented by mechanical movement and mechanical torque. The electrical output energy of the synchronous generator can be represented by these three-phase AC output voltage terminals connected to electrical load. The electrical load can be resistive load, inductive load, and capacitive load, or mix between resistive, inductive, and capacitive loads. In general, we can say that the synchronous generator is driven by a mechanical energy to supply electrical energy. In steady state, the speed of the machine shaft is fixed and can be called synchronous speed and can be denoted by Ns in revolution per minute RPM. The output electrical frequency of the generated output AC voltage and current represent the electrical frequency in Hz and can be denoted by small letter f. This output electrical frequency of synchronous machine is related to the rotor synchronous machine Ns by the following relationship: Ns equal to 120 F over P. As we can see, the synchronous speed Ns is related to the electrical frequency F and the number of poles of the machine. Synchronous machine is called synchronous because their rotor speed directly related to the AC electrical system frequency. In other words, the machine always operates or rotates in steady state at fixed synchronous speed that is related to the electrical frequency. We will learn later that the air gap magnetic field of the synchronous machine rotates at synchronous speed. That means the air gap magnetic field speed will be equal to rotor speed and both equal to synchronous speed. In practice, synchronous generators are interconnected, as shown, through transmission lines to share the load easily. It is interesting to know that all our electricity supplies in the homes, businesses, and industries are produced by synchronous generators installed in power stations. More than 80% of electrical power generated in the world is through synchronous generators. At large power stations, more than one unit of synchronous generator are connected in parallel. These synchronous generators generate electricity at fixed voltage and fixed frequency in steady state condition. Synchronous generators at the power plants are three-phase generators. The range of these generators is from 10 kW to 1000 MW for each unit. Now let's talk about synchronous motor. In case of synchronous motor convert electrical energy input to mechanical energy output. The input electrical energy can be represented by three-phase AC supply. The output mechanical energy can be represented by mechanical speed and mechanical torque supplied by the synchronous motor through the machine shaft to the mechanical load. The machine shaft connected to the mechanical load by using mechanical coupling. This mechanical fan shows an example of the mechanical load. Again, synchronous motor shaft rotate at synchronous speed Ns in revolution per minute RPM, and the synchronous speed is related to the input supply electrical frequency F by the following relationship: Ns equal 120 F over P in revolution per minute. Now we know that synchronous generator converts mechanical power or energy to electrical power or energy, Also, we know that synchronous motor converts electrical power or energy to mechanical power or energy. It is very interesting to know that besides this active power conversion between the electrical and mechanical power or energy, synchronous machine, whether motor or generator, can be used in power factor control or reactive power control of the electrical system. The beauty is that the control of reactive power is achieved by only controlling the excitation field current of the rotor field winding of the machine. The concept of power factor control or reactive power control is considered one of the most important concepts that we need to learn if we are planning to work in the field of electrical machines, electrical power systems, electrical drive systems, and grid-connected converters. So in general, synchronous machine can control the active and reactive power of the system. The details of the active and reactive power control will be covered in future lectures. Let's conclude this lecture at this point, and we will continue in the next lecture. Let me know if you have any question. Also, make sure to subscribe to this channel so you do not miss any lecture. Thanks for listening. I am Ihsan Al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.